So what are all the techniques we covered so far? The network provisioning, the first one, and then admission control, traffic aware routing, network throttling, right? And for network throttling itself, 3 ways of giving feedback: the chalk packet, explicit congestion notification, and hop by hop back pressure. So that is what we covered so far. Now the load shedding. So this is the last option, something we already had that congestion happened, and we are not helped with any of the techniques that we've seen so far. So this is a point where you are forced to discard the packets, right? So there is no other way, I can't handle, so that kind of a situation, right? So the load shedding is something in our normal power supply, this term will be familiar for you. So when we are running out of the electricity, maybe in the summer season, so what people will do, some area they will forcefully for some period of time the power supply will be interrupted, right? So by that they are trying to help the entire grid. So in that way, so this is the only way, as it is overly congested, we, even though we may taken all the precautions and all, we couldn't control things, so we are forced to discard certain packets. So that is the idea, the last thing, load shedding. So when none of the previous methods make congestion disappear, the routers can bring out a heavily artillery like load shedding. So load shedding is a fancy way of saying that when routers are being inundated by packets that they cannot handle, they just throw them away. So simply discard the packets which they can't handle. So this is something that is the last option when none of the previous methods make congestion disappear. So this you can depend as the last option, right? So the term comes from the world of electric power generation, of course, where it refers to the practice of utilities intentionally blacking out certain areas to save the entire grid from collapsing on say hot summer days when the demand for electricity greatly exceeds the supply, right? The key question for a router drowning in packets is which packet to drop. So drowning means overly congested router whom he is going to drop. So anyway, dropping is something mandatory. So the preferred choice may depend on the type of application that use the network. For example, if we are having file transfer application, the old packet is worth more than the new one. So whether you want old one or new one, you want old one when it comes to file transfer. Why? For example, this is because dropping say packet number 6 and keeping 7 to 10 is of useless, because this whether 6, 7, 9, sorry 6 we have in the queue we have packets like 6, 7, 8, 9, 10 all are part of a particular file, and still 6 the others were already correctly delivered to the destination. Now if you at a particular point you are forced to discard something, it is always preferred to discard the newly reached one, like the packet number 10. So in that order, 1, 2, 3, 4, 5 till 5 all the packets related to that particular file reach the destination, and 6 is the next one, and in the queue the latest one, the newly arrived packet is of course packet number 10. And at this point when the router is supposed to drop a packet, whether it will discard the packet number 6 or 10, right? The answer is always keep the older packets like 6, 7, 8 and 9, how much it is possible, and start discarding the new one. So that is the idea. Suppose you are doing differently, like you are not discarding this 10, instead you are discarding 7. What is the problem? Just look at the sender. It received 1, 2, 3 and 1, 2, 3, 4 and 5. Now it is waiting for 6. As 6 is discarded, 7, 8, 9 and 10 may reach. 7 through 10 may reach. But what is the use? Because and that file, that continuity will be lost, right? In between that 6 is lost. That is a mandatory. Even though that 7 to 10 is reached the receiver, there is no use. The only will only force the receiver to do more work to buffer, and what it has to do, the 7, 8, 9 and 10, it has to buffer and it has to wait for 6. Like that, things will be complicated. So better if you discard this 10 instead of the 6, that will be good. So that is with the applications like file transfer. Now if you look at a different applications, say real-time media. So just the opposite thing will happen. The new packet is always worth more than the old one. Why it is so? Because the packets becomes useless if they are delayed, because it's a real time application, so time bound is something very crucial. Same situation, 6, 7, 8, 9 and 10 in the queue, and the others reach at the receiver. So who you are going to drop? The what is suggested is the older one you drop, because this 6 will be having some time out. So if you discard the newer one and you try to send the 6, 7, 8, 9, they may suffer more delay, and altogether it may reach the receiver after the delay. So there is no use of the 6, 7, 8 and 9. So instead, if you are keeping this 10, maybe the time bound will be, still time is available for 10, but some time is already running out for 6, right? So I hope you can visualize what is happening. So always discard the older one, like the sixth one, and keep the newest one. So if it is delayed and the miss the time, which they must be played out the user, then there is no use, right? So keep that in mind. So the former policy, that is older one is better than new one, is what called the wine policy, where the later one, that the new one is better than old, is called the milk policy. Just like an analogy, because most people would rather drink new milk and old wine, right? So older one is better, so wine policy. Newer one is better, is what we can call as the milk policy. Just two terminology. So depending on the type of application, you have to decide whether you have to follow the wine policy or milk policy, or a combination of both, whatever it is. So that is something, the one decision making, like which packet to drop. Right, that is something application dependent. Now you can do this load setting, say a more intelligent way, or a more intelligent discard policy, we can see. So more intelligent load shedding requires the cooperation from the senders. So just like type of application you are going to discard, in addition to that, the sender can is having some role, in the sense it can prioritize a packet, like the normal packet and some special packet. The sender can try to prioritize, and accordingly it can inform, so that the intermediate nodes can do the action accordingly. So an example is packets that carry routing information, compared to the normal packets. So those which are containing the routing updates are something special, because if they are lost, the entire network connectivity is lost, or we are not getting the updated connectivity communication, right? So you have to consider them specially. In the queue, if a routing packet is there and normal packets are always there, always consider the routing packet special and give them a higher priority. So these packets are more important than regular packets, because they establish the routes. If they are lost, the network may lose the connectivity completely, right? So another example is that the algorithm for compressing video, say like MPEG, periodic, any compression software you can visualize, periodically transmit an enter frame and then send subsequent frames as a differences. So this is a normal procedure that is used by any compression procedure like MPEG. So when they start sending, there will be some reference frames, that is the first one which is being sent, and all the subsequent frames will be sent in such a way that they, instead of sending the frame as a whole, how the second frame is different from the first one, only that differences will be communicated. So everything is relative with respect to the first frame being communicated. That is the way, because most of the frames look same, so you don't have to send the end frame again and again. What you can do is send the first frame, and how the second frame is different, what are all the points where it is different, that you can communicate in the subsequent communication. So this is the idea used in MPEG compression particularly. So in that case, tell me whether it is the packet containing the difference information, or the packet containing the first frame, that is the enter frame information, is to be discarded. Of course, right, that enter information is something that is needed for everyone. So you always have to give a special preference to that one, and you can prefer discarding the difference packets if it is needed. So in this case, dropping a packet that is part of the difference is preferable to dropping one that is part of the full frame, because the future packets may also depend on that full frame. So full frame should be given some special priority over the other one, just like the routing backend. So in that way, the sender is now having the control, the one who is sending. It can be the actual user or the internet service provider who is sending your packets on behalf of you. Mostly this priority setting and all will be given to the administrative level people only. The normal we people are not supposed to change the priority. And in IP header again we will see how this which field is more modified for settling priority and all. So that priority you can adjust and accordingly you can handle this, right? So to implement an intelligent discard policy, application must mark their packets to indicate to the network how important they are. So this priority marking is something to be done by the application. So with that the router can choose the discard policy. So then when the packets have to be discarded, the router first drop the packets from the least priority class, then the next most important class, and so on. The discarding will happen, right? So that about the normal load shedding procedure. Now random early detection is something we can add as a better approach. Like you can make that load shedding more better by adding random early detection. So let's see what it is. So dealing with the congestion when it first starts is more effective than letting it come and then trying to deal with it, right? So always we want the remedy to be happen at the earliest. We don't want that thing to spread, and after that we don't have remedy. If we are applying remedy, the result will be less. So always try to do this congestion control at the earliest, right? As soon as you are getting some different behavior from the congestion, do it. So this observation leads to an interesting twist on the so-called load shedding procedure that we learned so far. So what is that twist, right? Which is to discard packets before all the buffer space is really exhausted. Normally we are discarding. So this is something I think you just try to listen, because TCP is something we didn't cover. To understand it fully, that TCP knowledge is also needed. But anyway, I will try to explain maximum. So more clarity you will get after covering TCP protocol. Anyway, so somewhat linked with that. So the idea is like normally when you will be discarding, when the buffer is exhausted, right? So full, at that time you can start discarding, but as a last option. But now we are doing it slightly different, like we will discard the packets before all the buffer space is really exhausted. So just before the exhaustion point or just before reaching some kind of threshold, we started discarding the packets. So why we are discarding before the actual problem? So you may be wondering, right? So there is something special about it. Just listen. So motivation for this idea is that the network hosts do not yet get congestion signal from routers as explicit congestion notification. So normally if you depend on the explicit congestion notification techniques like ECN or chalk packet or that kind of things, there are certain problems like what about the IP package itself is not providing any guarantee. So that is something a problem with this explicit congestion notification. So instead we are trying to inform the sender about the presence of a congestion. One way is by means of chalk packet or ECN, but another way you can inform the sender the presence of congestion. Actually we are trying to do it lit early, like just before the actual exhaustion, just before the point the routers are actually exhausted, we are sending we are discarding the packet. So why we are discarding packets? Discarding packet is actually or the lost packet is a very good effective way of communicating the sender that something wrong happened. So if my packets are lost, I will not get the acknowledgement. So there are two ways I will not get acknowledgement. One thing is, of course, it is lost. Another thing is some error with my packet. But in wired network content, mostly the chances of error is very, very less. So always there is no acknowledgement means. Particularly if you are using a transfer layer protocol as TCP, it is very much careful about such scenario. If there is no acknowledgement, the indication is that the packet is lost and that is due to congestion. So like that the sender will conclude. So that is a catch there. Just focus. So instead, the only reliable indication of the congestion, right? Explicit congestion notification you can depend for congestion indication, but of course this is an IP packet. This is communicated through the normal IP packets or a special chalk packet, the ICMP source packet. These things are actually not reliable. That we will see the network layer protocol like IP is not reliable. So that is the thing. So a more reliable in the sense we are not taking any extra care. If it is lost, that's all. But if you are looking at transport layer protocol like a TCP, you can say that it's more reliable in the sense it's taking some additional effort for reliability. So something you may understand more after covering those things. But anyway, this is a more reliable indication of the congestion is actually packet loss, right? So like that you can conclude at this point. So definitely if it is packet loss, there are two cases. I mean, I am not getting, I sent something, right? Let me visualize like A sends something to B, and B is supposed to give an acknowledgement back. Suppose A didn't get this acknowledgement. There are two cases. Either what is sent by A is dropped on the way, right? I mean it is lost, it indicates the packet loss, or it is acknowledgement is not given by B because some error happened with the data, it is erroneously received. But in a wired network typically the chances of error is very less, so chances are very high for the packet loss. So like that the sender will conclude that this is packet loss, and packet loss is of course due to congestion. So it is more reliable way of indicating the sender about the presence of congestion than things like explicit congestion notification. So right, hope it is clear. Now after all, it is difficult to build a router that does not drop packets. So definitely that whenever there is overloading, the routers are supposed to drop packets. So that is a usual scenario. So like that the device will conclude. So transfer protocol like a TCP is hardwired to react to loss as congestion. So whenever there is loss, packet loss, TCP by default believe that it is due to congestion. Showing whenever there is loss due to congestion, definitely the sender is supposed to slow down the speed, right, the response. So the reason behind this logic is that TCP was designed particularly for the wired network, and in a wired network they are very reliable in the sense, so the packet losses are mostly due to the buffer overflow or because of congestion rather than the transition error. This is what I was trying to say. In a wired network the chance of error is less or it is more reliable, so packet loss, that is directly it can be linked with the congestion. So this is what TCP is typically doing. So accordingly, whenever there is congestion, packet loss, and it will observe, and using a particular special procedure, it will slow down the data rate. The rate at which the sender is sending. So that we will see maybe when we discuss TCP. So wireless links must recover transmission errors at link layer to work well with the TCP. So this is something, if you want to use TCP for wireless link situation is entirely different because chances of error is very high. So error handling should be done at some lower layer to make it work with the TCP, because at that TCP layer it has to assume that if there is loss, the acknowledgement is not coming by, that is due to loss. In that way only TCP will work. The other possibility of error, transmission error, will be ignored fully. So wireless link you can't ignore that much. So that is why if the errors are there, that should be dealt in a different way at the link layer. Yeah, so this situation can be exploited to help to reduce congestion by having routers drop packets early. So what we are doing, we are forcing the routers to drop packets early just before the actual problem occurs, right? So by forcing packets early in a selective way, before the situation has become hopeless, there is time for the source to take action before it is too late. So now we are giving enough time for the source, like the situation is going to be congestion, you take precaution, just like that we are having some time gap in between. Otherwise once the problem started, things will go beyond our control. So we are taking some kind of precaution by detecting things early. So randomly we are detecting certain packets and we are choosing, and we are choosing them as a good candidate, and we are forcefully dropping them just before the actual congestion happen. So a popular algorithm for doing this is called random early detection. How this random early detection is working is something a very big topic actually, and that we are not covering here. So just understand that this kind of a procedure is being used in random early. So it's having more theoretical background, so that you can read in some advanced textbook anyway. So that's the type of algorithm we are using for doing this task, that checking that the situation is going to be congestion or not, and accordingly selecting certain packets randomly and early and dropping them, right? So to determine when to start discarding, the routers maintain a running average of their queue length. So it is something that again depends on the queue length. So queue length is again going to be a measure of congestion. So queue length is going beyond some threshold value. You can see that a congestion is yet to start, and that time you can randomly pick some packets and you can drop them. So when the average queue length of some link exceeds some thresholds, this threshold everything you have to carefully choose. Exceed that threshold value, the link is said to be congested. It's going to be congested, and a small fraction of the packets are forcefully dropped at random. Again, that randomness makes sure that the fast sender is going to be slowed down, right? Because the most of the packets in the queue will be from the fast sender. So definitely once you pick a packet randomly, the chances are very high for the one which is being sent by the fast sender is being picked, and accordingly the fast sender will be getting a congestion notification. So picking packets at random makes it more likely that the fast sender will see a packet drop at the earliest. So this is the best option, since the router cannot tell which source is causing most trouble in the datagram network. So random picking is we are hoping that it will help with a very good probability, of course. So affected sender will notice the loss when there is no acknowledgement back, and the transport layer will start slowing down the data transfer. So the lost packet is thus delivering the same message, just like a chalk packet or explicit congestion notification, but now the things are happening implicitly. So the loss is implicitly taken by the sender to be an indication of congestion. That is the thing. So random early detection routers, the router having this algorithm running, improve performance. So a router with a red algorithm improve performance compared to the router that drop packets only when their buffers are full. So though they may require tuning to work well. So compared to other routers, they works better, but some kind of tuning is needed, in the sense, for example, the ideal number of packets to drop. So because this is actually not a needy process, so who is to be dropped, how many packets are to be dropped, everything you have to tune properly, and what about the threshold value, everything, right? So that is a difficulty there. So a very good statistics is needed for all those process. So the ideal number of packets to drop depends on how many senders need to be notified of the congestion. So all those parameters has to be tuned properly. However, the same random early detection in the sense that congestion explicit congestion notification also you can send instead of dropping the packets, just like you notices that when the average queue length is beyond some threshold, you understood that the congestion is yet to start. At that point, instead of picking some packets randomly and dropping them, another way you can depend is the same ECN procedure. You can tag the certain bits of the, you can mark certain bits of the outgoing packets, and you can try to warn the sender. But the problem with the ECN is we can't trust it, right, as it is an IP packet. So it works in exactly the same manner, but delivers a congestion signal explicitly rather than an implicit notification by the lost message. So that is used when host cannot receive explicit signal. So this kind of an explicit signaling, when we are not sure about its guarantee, we can go with the random early detection, the pure dropping procedure. So that about the load shedding procedure and its variation with the random early detection routers, something like that. Okay, hope it is clear. Or yeah, thanks for watching. Still doubts will be there that we can clarify in our discussion class. So that about congestion, we were stopping the topic congestion at this point. Maybe in the next topic we will start a different next video we will start a different topic. Yeah, thanks for watching.